Okay, in this video, I'm going to teach you about a variation on induction called strong induction. And it's similar to induction, but there's one important difference. So when we establish the statement that we want to establish, so I'm just going to use capital S for statement n plus 1, sub n plus 1 to mean like whatever statement we're trying to prove at the n plus 1 level, um, we can use S sub n, which is what we've been doing, the S statement at the nth level. But also, this is what makes it strong induction. We can also use S sub 1, S sub 2, S sub 3, all the way up to Sn minus 1, i.e. all previous statements. And you should check out principle 4.7 from the book on this. But the idea is the following. What we've been doing, we say, let's establish the base case. Let's establish the first rung of the ladder. And then let's establish that we can continue to climb the ladder, right? Meaning, if I'm at the nth rung, I can go to the n plus first. If I'm at the 10th, I can go to the 11th. If I'm at the millionth, I can go to the million plus 1. Okay? Great. That's what we've been doing with induction. But now it's like, if I'm at the millionth rung in the ladder, then that means every rung below it, 1, 2, 3, 4, 5, so on and so forth, up to a million, has been established. So if I want, I can use any of those previous rungs of the ladder. So that's what strong induction says. And you only do this if you have to. So you should want to see now an example of why you would have to do that, right? So the theorem that we're going to prove using strong induction is a very important theorem in mathematics. It's called the fundamental. Anytime a theorem has fundamental in it, it's important for obvious reasons. That's why the name is there. Fundamental theorem of, this one's the fundamental theorem of arithmetic, which says the following. So you've probably seen this before, or you've maybe not seen it as a theorem, but you've definitely used it in some fashion before. So for every natural number, bigger than or equal to 2 to avoid the 1 case, is either prime or a product of primes. I think I've even already said this before in class, but we never proved it. So here we go. And again, let's just play around a little bit before I prove this. So let's just remember some of our prime numbers here. We have 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, so on and so forth. And actually, in number theory, people study the prime numbers quite a bit and the distribution of the prime numbers, so on and so forth. It's very interesting stuff. But then for any other number, break it down, right? So 35 is like 5 times 7. 100 is like 2 times 2 times 5 times 5. 12 is like 2 times 2 times 3. And 99 is like 3 times 3 times 11. Notice 99 to 100, these are very close numbers, of course. They're only differ by 1. But their factorization is not similar really at all. 100 is 2 times 2 times 5 times 5, and 99 is 3 times 3 times 11. So not only the number of factors is different, but every single factor is different. So there's no reason to think that regular induction will work here. Going from 99 to 100, there's no reason why you'll be able to relate the 99 case to the 100 case, right? So we should immediately notice that that's not going to work, just for the observation we see from going from 99 to 100. And if you play around with other numbers that differ by one in their factorization, you'll see that there's no good pattern there between a number and one plus that number plus one. There's no good sort of observation. So that's why we're going to need strong induction. But at this stage, we don't even know that induction will work at all at this point. So let's see what happens. So um, we will assume that for in that for every k natural number such that 2 less than or equal to k less than or equal to m um, is either prime or a product of primes, and show that n plus 1 is either prime or a product of primes. So when we state the strong induction hypothesis, we still go from n to n plus 1, but now when we're stating things about n, we're saying for all natural numbers that are less than or equal to n, and we have to go all the way down to the base case. So between the base case and the case we're on right now, we can use any of those to prove the next case, right? So let's see. So either m plus 1 is prime, and we're done, right? Then we got lucky and we're done. Or now this is not we're not using the inductive hypothesis here. We're just saying if you're not prime, then you can be written as the product of two smaller numbers, right? So or m plus 1 is equal to s times t. I'm not saying these are prime, where s and t are natural numbers. They are not equal to 1 because then we wouldn't need them as factors. And they are strictly less than n plus 1 because they're factors of n plus 1, right? But then now we can apply the strong induction hypothesis, right? Because the point is that then both S and T are in the range that we've assumed already works. They're smaller than n plus 1, they're bigger than 1, they're natural numbers. So each of S and T are in the range that we've already assumed works. So each S and T can be written as a product of primes, and n plus 1 is equal to a product of two things which are each equal to a product of primes. So the entire thing is equal to a product of primes. Okay, so now we're going to just go into the proof because we were just doing the sketch. We don't want to, now that we understand the idea, we don't want to do the sketch anymore. So let's go into the actual proof. And now we say we proceed by strong induction. So we're just going to let the reader know that we're using strong induction. Sometimes I think later on, and when you're doing proofs, we just kind of like say induction and we mean, either strong or regular induction. Sometimes we are more careful about that, but at this point in your math proof writing careers, you should make a distinction between these two things until you become very familiar with it. So let's start with the base case, which almost feels kind of silly here. So the base case is n equals 2, and it almost feels silly to say anything, but we should just say something since 2 is prime. We are done. 2 is equal to the product of primes because it's just prime. Okay, perfect. Now we go to the inductive case. let n be a natural number which is bigger or equal to 2, and assume that I'm going to write it slightly differently than we did in the proof sketch. Assume that 2, 3, 4, all the way up to n minus 1 and n are either prime or a product of. Okay, then we'll tell the reader what we're going to do now. So we aim to show the claim is true for m plus 1. Okay, so I'm going to break it into cases. We could just write it in the paragraph. So the first case is that m plus 1 is prime, and we are done. Okay, we got lucky because it's already prime, and we're done right away. Okay, but now case 2 is where the action happens. So here is m plus 1 is not prime, so another way of saying that is divisible by s in the natural numbers where s is not equal to 1. Right? Because if you're not prime, then you have to be divisible by something. And so hence there exists some t where t is also not equal to 1, so that m plus 1 is equal to s times t. We know that 1 is strictly, we already said that part, but s and t are in this range, and hence satisfy the inductive hypothesis. Okay, so that means so s and t are either prime or a product of primes, and hence m plus 1 is a product of primes. Perfect, right? Because again, s and t, maybe s and t are both prime. Perfect, that's a product of primes, right? But and maybe only s is prime and t is a product of primes. Doesn't matter. Either way, we're going to get a product of primes for m plus 1. And so now we'll just say to end the proof by strong induction, this must be true for all natural numbers where n is bigger or equal to 2. And that's the end of the proof. So that's our first example of strong induction. And now we'll see a few more examples of strong induction.